Okay, so hopefully from the experiment that we've conducted over the last couple of days, you came to the conclusion, or at least between you and the groups around you, you came to the conclusion that of the three quantities we considered, velocity is not always conserved during a collision. Kinetic energy is not always conserved during a collision, but with a few exceptions that you probably had because of friction and the tilted tabletop and some other areas of uncertainty and not selecting the right part of the graph. There may have been some other times where momentum was not conserved, but hopefully as a general trend, you saw that linear momentum was conserved great majority of the time in the collisions, at least far more frequently than velocity or kinetic energy. And so today we want to consider why that is, and then use what we learned in the experiment to apply to how to solve problems involving collisions where we consider the linear momentum. And so to explain why, I did this thought exercise in class, and that is, let's imagine a 12 kilogram ball that's moving 3 meters per second, and it's about to collide with a 4 kilogram ball moving at 6 meters per second in the opposite direction. So they're going to collide head on. And the question I have for you is, what will be true about the magnitude of the forces that they exert on each other? FAB is the force that is exerted on ball A by ball B, and FBA is the force on ball B by ball A. And so the question is, which of these symbols should go in between there? Will they be the same force on each other? Will B push harder on A than A pushes on B? Or will A push harder? And so I'll give you a second to pause and think about that, come up with your own answer. So hopefully you've given that some thought, and maybe you have some justification for which of those options it is. But the right answer is that they're the same. And the reason that they're the same, quite simply, is what we refer to as Newton's third law. And of course, Newton's third law says that if object A pushes on object B, then object B will push in the opposite direction with an equal magnitude on object A. And that's a law, so there's no exception to that. And so as they collide, they're going to push on each other with the same amount of force. And so then the follow-up question I asked is, well then, which one will be a greater time? Will object B exert its time, or its force on object A for a longer time, or will object A exert its force for a longer time on object B, or will those be the same? I'll give you a second to think about that. And of course, the answer to this is maybe a little more intuitive, but that is those are the same as well. And again, it comes back to Newton's third law. If object A is pushing on object B, then object B at the same time is pushing on object A, and so one can't push on the other without the other pushing back. And so you say, well, so what? Well, if those are true, if the forces exerted by A on B and B on A are equal in magnitude and opposite in direction, and the time that they push on each other are the same, then we get this interesting phenomenon. And that is, if we take Newton's second law, which, as you know, is that the acceleration is directly proportional to the net force and inversely proportional to the mass of the object, and we substitute the definition of acceleration, change of velocity over time, and cross-multiply, we get what we've already worked with this year, that is the impulse momentum theorem. Force times time equals mass times change of velocity, and that mass times change of velocity is what we would call a change in momentum. Of course, the symbol for momentum being lowercase p. And so if we consider what we just said, and that is that the force that A exerts on B is equal in magnitude and opposite in direction as the force that B exerts on A, then each of them are going to have the same force acting on them, just in opposite directions. And if they act for the same duration of time, the same period of time, then they're going to have equal and opposite impulses on each other. And if they have equal and opposite impulses on each other, then the total change in momentum for the entire system has to be zero. Well, if the total change in momentum of the system is zero, then that means the total momentum before the collision and the total momentum after the collision have to be equal. And that's what we that's the conclusion we drew, right? That in these collisions, the momentum before equals the momentum after when added up as vectors. And of course, this assumes what we call a closed system, or a system with no outside unbalanced forces. But for any closed system, the linear momentum then will be conserved for any type of collision. That is, all types of the collisions. And you experimented with it, several different collisions in your lab. But let me now just define what we refer to as 4 major types of collisions. And they are defined based on what happens with kinetic energy. First of all, we call one type of collision elastic collision. An elastic collision is one in which the kinetic energy is conserved. In other words, the total kinetic energy before equals the total kinetic energy after. Then, of course, if there's elastic, there must be inelastic. And inelastic means that some kinetic energy is lost. It doesn't have to be all the kinetic energy, although it can be, but it just has to be at least some of the kinetic energy is lost. In other words, the final kinetic energy is less than the initial kinetic energy. Then we have a special category within inelastic that we call perfectly or totally or completely inelastic. And in that case, kinetic energy is lost, right? It is inelastic, but then there's a second qualifier, and that is that the objects have to have the same final velocity. So usually your clue here is that the two objects stick together, or they become one, or they latch on to each other so that they end up moving together with the same final velocity. And then the 4th type of collision is the weird one. It's called superelastic, and that's one in which kinetic energy is gained. And common examples of this are like a firework, or firing a gun, or unleashing a spring. There's some kind of stored energy, whether it's chemical or elastic or whatever, and as a result, the objects after the collision have more kinetic energy than they started with. So let's work some practice problems and then look at an approach that we can use on these collision problems. So here's an example. A 6-kilogram ball is traveling 3 meters per second to the right when it collides with a 4-kilogram ball originally at rest. If the collision slows the 6-kilogram ball to 1.5 meters per second, what will be the final velocity of the 4-kilogram ball? So like we learned early on with kinematics, the first thing I'm going to encourage you to do is identify all the given and unknown information. And so if I take a look, I've got the mass of the first object and its initial velocity, and I've got the mass of the second object and its initial velocity, which is 0 because it's at rest. And then I've got the final velocity of the first object, but I'm looking for the final velocity of the second object. And so let's apply what we just learned to figure out how fast this 4-kilogram ball is going after this collision. And I'm going to encourage you, like I did, again, with all the other types of problems we solved, to sketch yourself a little diagram, a little picture. And so I always label it before, and then I say that the 6-kilogram ball is moving 3 meters per second to the right, and I've indicated that. And the 4-kilogram ball is initially at rest. And then notice, momentum and velocity are vector quantities, and so I've got to be careful with the positive direction. So I'm going to explicitly label, in this case, that the right is positive. Okay, so now let's apply that equation that we just learned. If this is a closed system, which all the problems I'm going to give you this year are going to be closed systems, and so the collision is going to have linear momentum conserved. But if it's a closed system, then the total momentum before has to equal the total momentum after. So let's find that total momentum before. And the way we do that is we're going to add up all of the momenta of the different objects. And so, for example, mass 1 times its initial velocity is its initial momentum, and mass 2 times its initial velocity gives us object 2's initial momentum. So when I add those up, 6 times 3 plus 4 times 0, I get the total momentum before the collision of 18 kilogram meters per second. And so that's the total momentum before the collision. Now, I'm going to now look at the conditions after the collision and sketch myself a picture of that, where I see that the 6 kilogram object is still moving to the right, but it just slowed down, and it slowed down to 1.5 meters per second. And the unknown information, of course, is that final velocity of the second object. So I'm going to write out that statement again to find out what the total final momentum is. It's the mass of the first object times its final velocity plus the mass of the second object times its final velocity. I know V1 final, which is 1.5. I don't know V2 final, so I'm just going to leave that as a variable. And I get 6 times 1.5 plus 4 times whatever the final velocity of the second object is. Now remember, the momentum was conserved in this collision, and so whatever the initial total momentum is, has to be equal to the final total momentum. So I know that the final total momentum has the value of 18. So I set 18 equal to 6 times 1.5 plus 4v, and then I can solve for v. And algebra tells me that it ends up being 2.25 meters per second. Because I ended up with a positive number, I know it's moving in the positive direction, and so since I asked for the final velocity, it needs a direction, and so I'm going to state that as 2.25 meters per second to the right. And like I've said all year, basically let's explicitly state with words the direction to the right, even though I've put a positive arrow to the right, just to make sure that everybody's clear on what that direction is. All right, so then the other thing we want to ask is, well, then what type of collision was this? And to know what type of collision it was, we need to compare the kinetic energies before and after the collision. And so I'm going to add up the kinetic energies before the collision, which is, of course, 1/2 mv squared initial for both object 1 and object 2. And I'm going to do the same thing for after the collision. And then I get this, right? 1/2 of 6 times 3 squared plus 0, because the second object has no kinetic energy before the collision. And that gives me 27 joules of kinetic energy before the collision. And then 1/2 of 6 times 1.5 squared plus 1/2 of 4 times 2.25 squared gives me a total of 16.9 joules of kinetic energy after the collision. Well, how do those compare? Well, it went down, right? So the final kinetic energy is less than the initial kinetic energy. I could say that kinetic energy is lost, and so I call that an inelastic collision. All right, so let's work another example. So this one says a 15 kilogram ball is moving 3 meters per second, and it collides with and sticks to a 10 kilogram ball initially at rest. And the question is, how fast will the balls be moving after the collision? Well, once again, I'm going to identify what's given information. I know mass 1 is 15 kilograms, mass 2 is 10 kilograms, velocity 1 initial is 3 meters per second, velocity 2 initial is 0 because it was at rest. And then it says, how fast will they move together? Well, they stick together, and so they're going to have that same final velocity, and so there is just one final velocity. So let's sketch it real quick. We've got before, the 15 kilogram ball is moving to the right 3 meters per second. The 10 kilogram ball is initially at rest. I'm going to make the right direction positive just because it's simple and makes sense to me. And then I'm going to find out, well, then what was the total momentum before the collision? I add up those two momenta, m1 v1 initial plus m2 v2 initial. 15 times 3 plus 0 tells me that the total momentum before the collision was 45 kilogram meters per second. Now I turn my attention to after the collision and sketch myself a picture there. Well, they're going to stick together and move together, and so like I said, there's only one final velocity, and now they have one total mass. So what is that momentum? Well, I'm going to say that it's m1 times v final plus m2 times v final, but since they're the same v final, I can factor that out and basically just add up their masses and multiply that by v. So the total momentum after the collision is going to be their total mass 25 times their final velocity v. Once again, because momentum is conserved, I know that the final total momentum has to equal what the initial total momentum was, which was 45. And I set 45 equal to 25v, and then solve for v. And v tells me that it's 1.8 meters per second. Now notice I just asked how fast, and so I don't have to specify the direction, but of course they are going to move to the right because that was the direction that the first ball was moving before the collision. Then I ask, well, what kind of collision is this? So I have to compare the kinetic energy before and the kinetic energy after. Of course, before the collision, only the 15 kilogram ball has kinetic energy. Afterwards, they together have a combined kinetic energy. And I see that the total energy before was 67.5 joules. The total energy after is 40.5. And once again, the total energy went down. The initial kinetic energy was greater than the final kinetic energy. And that doesn't surprise me because, number one, we just showed with numbers that kinetic energy was lost, and so therefore it's inelastic. But then I could have predicted that because they stuck together and had the same final velocity, which we've said is a special kind of inelastic collision, one that we call perfectly inelastic. So anytime two objects stick together and become one, it has to lose kinetic energy because that's a perfectly inelastic collision, or totally or completely inelastic. You'll hear all those adverbs used. But for all of them are specific types of inelastic collisions, and so kinetic energy will be lost. But then, we oftentimes will ask how much, and so you'll have to actually do the math to figure it out, what the kinetic energy before and after was. All right, so now let's do another example. And now what I'm going to encourage you to do now is to, go ahead and, of course, pause the video at different times to do the different steps on your own, and then resume the video to test yourself or check yourself. But basically, here we have an 8 kilogram ball traveling to the right at 6 meters per second, and it collides head-on with a 10 kilogram ball traveling 4 meters per second to the left. If I say that the 8 kilogram ball rebounds going 2 meters per second, what will be the final velocity of the 10 kilogram ball? So again, give it a shot on your own, and then just resume the video periodically to see how you do. Of course, the first thing I'm going to do is I'm going to identify all the given and unknown information. I have mass 1, mass 2, initial velocity 1, initial velocity 2. But then there's some other information that's kind of hidden in here in the words head-on and rebounds that I'm going to have to be careful of because, again, these are vector quantities. So just to help myself out, I'm going to sketch a quick diagram of before. And you notice that the 6 meter per second to the right of the 8 kilogram ball is in the opposite direction of the 10 kilogram ball, moving 4 meters per second to the left. So again, it's going to be very important that I specify the positive direction. I'm going to choose right as positive. You could work it left as positive and get the same answer, but I'm just going to go with right. And then that's going to change how I do the math when I calculate the total momentum. I still do M1V1 and M2V2 initially, but notice the V2 initially is moving to the left, and I designated the positive direction to be to the right. And so when I do 8 times 6, I'm going to add that to 10 times negative 4, because the 10 kilogram ball was initially moving in the negative direction. So that gives me a total momentum of 8 kilogram meters per second. Well, once again, if momentum is conserved, then that's going to be the final total momentum as well. So let's sketch the final situation after the collision. The 8 kilogram ball rebounds. Now, that important word rebounds. If it rebounds, it changes direction. So notice I've drawn it going back towards the left at 2 meters per second. And then the question is which way and how fast is the 10 kilogram ball going? Notice I don't have any direction arrows because we've got to figure that out. So I plug it in. I know that 8 times negative 2, because it's moving to the left, plus 10 times V final, whatever that is the total momentum after the collision. Well, what is that total momentum have to be equal to? It has to be equal to what the total momentum before the collision was, which was 8 kilogram meters per second. So I say 8 equals negative 16 plus 10V. And then I solve for V final, and I get 2.4 meters per second. Now, did I get positive 2.4 or negative 2.4? Well, the algebra tells me that it was positive 2.4, and so I know that it's moving in the positive direction, which I determined was to the right. Now, again, obviously you could have made left positive, and in this case you would have gotten a negative number for the 2.4, which again still indicates to you that it's moving to the right. So what type of collision is it? Well, let's compare the kinetic energies. The kinetic energy before, the kinetic energy after. Now notice, kinetic energy is a scalar quantity, and so I don't have to worry about the directions. But when I plug into 1/2 mv squared for both of these objects before and after, I get that it's 224 joules total before the collision, 44.8 joules after the collision, and so once again, it went down. The initial kinetic energy total is greater than the final kinetic energy total. And so we call that an inelastic collision because kinetic energy was lost. All right, two more. This one, a 5 kilogram ball is traveling east at 3 meters per second when it collides with an identical ball initially at rest. If the collision stops the first ball, what is the final velocity of the second ball? Again, pause, identify your given information, and actually see if you can work the whole thing before resuming. So here's your given information. 5 kilograms is mass 1, and then I said it's an identical second ball, so mass 2 must be also 5 kilograms. Object 1 was initially moving 3 meters per second towards the east, and object 2 was initially at rest. The collision stops the first ball, so its final velocity will be 0, and I'm looking for the final velocity of the second ball. Sketch yourself an image. I'm going to make to the right or east the positive direction, 3 meters per second east for the 5 kilogram ball. Gives me a total momentum before the collision of 15 kilogram meters per second to the east in the positive direction. Sketch the after situation and notice that the first ball stops, the second ball keeps going or starts going, and the question is, how fast does it go? Well, the total momentum after then is 5 times 0 plus 5 times whatever v final is. What does that have to equal? Well, because the momentum is conserved, that has to equal 15. 15 then equals 5 v2 final, and therefore v2 final is 3 meters per second in the positive direction, which I determined was east. And so the final answer is 3 meters per second east. Well, what type of collision is it? Determine what the initial kinetic energy was and the final kinetic energy, and you get that they're the same, 22.5 joules each. So this is the first time that the two kinetic energies were equal, which we said is what kind of collision? Elastic. And so since kinetic energy was conserved, this is what we call an elastic collision. And the most common real-life example of near elastic collisions is like pool balls, right? When you hit two identical mass pool balls, when you hit the cue ball into the 8 ball, oftentimes the cue ball will stop and the 8 ball will move off with the exact same, or very close to the same velocity. Obviously, it's not the exact same because you hear the collision, and so you know some energy was lost, but it's pretty darn close to being elastic. All right, last example. A 12 kilogram ball and a 3 kilogram ball are initially at rest on opposite ends of a compressed spring. When they're released, the 12 kilogram ball moves 2 meters per second to the left. What is the final velocity of the 3 kilogram ball? And so you can probably anticipate that this is going to be that weird type of collision. It's almost like its own kind of explosion. And so identify the given information, mass 1, mass 2, and then both of them are initially at rest. So they both have an initial velocity of 0. I give you the final velocity of the first ball, and I ask for the final velocity of the second one. Well, sketch yourself a picture. Before the collision, the 12 and the 3 are compressed against this spring, and they're not moving. And then I choose a positive direction, because obviously with vector quantities, I got to worry about the direction. And then I do a momentum calculation. Well, they both have an initial velocity of 0, so neither one of them has momentum before the collision, and so therefore the total momentum has to be 0. Sketch myself a picture of what happens after. The 12 kilogram ball moves to the left 2 meters per second. What's going to happen with the one on the right, or the second ball? Well, what does the total momentum have to be? Because momentum is conserved for all types of collisions in a closed system, the total momentum after the collision has to be 0 again. And so there's the total momentum, 12 times negative 2, right, because it's moving in the negative direction to the left, plus 3 times v has to equal what? It has to equal 0. And so 0 equals negative 24 plus 3v. Algebra tells me then that the v2 final is 8 meters per second. It's a positive value, which means then it's moving to the right, which again makes sense. If the total momentum before the collision was 0, and one ball moves to the left, and the other ball has to be moving to the right. But they're not going to move with equal speeds or equal velocities because they have different masses. And of course, again, the most important thing to remember is that the momentum is always conserved, not the velocity or necessarily the kinetic energy. So again, speaking of kinetic energy, what type of collision is this? Well, let's sum up the kinetic energies before. That's easy, it's 0. Sum up the kinetic energies after, 1/2 mv squared for each of those two objects gives me 120 joules. And look what happened. It gained kinetic energy. The kinetic energy went up. And therefore we call that a superelastic collision.